These are selected homework problems from Chapter 1.4a, Continuity and One-Sided Limits. So number 7, limit as x approaches 5 from the right side of 5. See that plus there. Of x minus 5 over x squared minus 25. Now, whenever you're dealing with one-sided limits algebraically, you're going to evaluate these one-sided limits the same way that you do with previous limit problems. All right, you're still going to go through your steps. You're still going to plug in, simplify, reduce, and then replug in. The only time that these one-sided limits is going to be treated differently is if all of this still ends up giving you does not exist. So if it then does give you does not exist, then we can look at some other steps to help us figure out what the one-sided limit is. But initially, many times, your answer will look the same as a normal limit problem. So in this case, we're going to ignore that the one-sided limits property for now. We're just going to deal with the 5. So first thing we do with limits, we always plug in our target x value. We get 5 minus 5 over 25 minus 25, 0 over 0. Now 0 over 0, algebraically, that indicates we can do something more with the expression, finding common factors, simply simplifying and reducing. So in this case, denominator can be factored to x plus 5, x minus 5. The x minus 5 cancels out. And now we can try replugging in the x value of 5. 5 plus 5 is 10, so our limit is simply 1 over 10. Okay, so we get a real number answer. There's no need to do anything different. So in this case, for our purposes, the one-sided limit is going to give us the same answer as if we were just finding the limit as x approaches 5. Okay. Now, number 9 is something that we have to do something a little differently. Now, when the limit does not exist, then we have to evaluate the one-sided limits a little further and determine whether it's going to be positive or negative infinity. So in this case, limit as x approaches negative 3. First thing we do is we can just plug in our x value. We're going to get 0 over 0. So that indicates we have to further figure out what type of solution we're going to get. Now 0 over 0 tends to mean that we can factor out a little further and simplify, but in this case, root x squared minus 9, we can't find any common factors to cancel out, so we're going to resort to determining what type of or where the graph is heading, because we see that this might be a vertical asymptote. So negative 3 from the left side of negative 3 means that we want to be testing values that's close to negative 3 to the left of negative 3. So if we choose negative 3.01, then we can just test to see what the signs are. If we get a positive over positive or negative over negative, we're going to be expecting positive infinity because we know there's vertical asymptote there. And if we get a negative or positive over negative, then we know that there will be that the graph will be approaching negative infinity. So in this case, we're going to get negative over a positive because negative 3.01 squared minus 9 will give us a positive value. Square root of positive is still a positive. Negative over positive is negative. So we see that the limit as x approaches negative 3 from the left side of negative 3 will be negative infinity. Okay. Right, limit as x approaches 0 from the left side of 0, there's number 11. We can always write absolute value as a piecewise function. So I can write this as x over x and also negative x over x. So I have the positive version of the absolute value and the negative version of the absolute value. So I'll get 1 if x is to the right of 0 and negative 1 if x to the left of 0. So this is what our graph will look like. Now if we look at this graph, and if we're approaching 0 from the left side of 0, we're going to see that the graph is going to be approaching negative 1. We can also plug 0 into the piecewise function that matches its domain, and that would also give us -1. Okay, 31, we have a piecewise function, 3 minus x and 3 plus 1/2 x. We want to find out whether the function is continuous. So first condition is going to pass because first condition f of 0 will be 3. And then we can find the one-sided limits to determine if the second condition passes. And limit as x approaches 0 from the left side of 0, we're going to get 3 minus 0 is 3. Plug in 0 to the right side of the to the other piecewise function, we're also going to get 3. So since the limit exists, our function is continuous because it passes the first condition, passes the second condition, and the third condition also passes because the order pair exists where the limit exists. Okay, 37. Trying to determine where or what type of discontinuity we're going to get. So if we look at this, we can factor the denominator. We get x times x minus 1. The x's cancel out. We know that there's going to be a hole at x equals 0. And we know there's going to be a vertical asymptote at x equals 1. So the hole means we have removable discontinuity at 0. The vertical asymptote means we have non-removable discontinuity at x equals 1. Okay, 43, again, absolute value, we can always treat these like piecewise functions. So the point where the graph is going to have a break could be at -2. So we can say we have the absolute value. We can take the positive version of the graph of the absolute value, and this is where x is to the right of -2. And then we also have a negative version, so negative x plus 2 over x plus 2 if x is less than -2. So this reduces to be +1, this becomes -1, so we have a graph that looks like this. And so there's a disconnect. We know there's going to be a non-removable discontinuity at x equals 2. X equals -2. Okay, 47, we can test what type of discontinuity it is by going through our conditions. So first condition, does the order pair exist? F of 2 is the first piecewise function, so 1/2 times 2 is 1, plus 1, which is 2. So we know the order pair is at 2, 2. Does a limit exist? So we find the limit as x approaches 2 from the left side of 2. So this is referring to the branch that is leading up to 2 from the left side of 2, so that's talking about this branch. So if I plug 2 in here, I'll get 2. Limit as x approaches 2 from the right side of 2 is talking about this branch. So 3 minus 2 is 1. 2 does not equal to 1. Second condition fails. So therefore limit does not exist. And if second condition fails, we know this is going to be a non-removable discontinuity.